Hi, this is Tony Northrop for TrainSignal, and in this video lesson, I'm going to be discussing remote access technologies for the SSCP certification exam. Up first, let's talk about the major different remote access architectures. This is the classic client-to-server architecture. Lots of different clients and usually one or a group of servers that they all connect to. This is specifically for the VPN. So what you'll see is all these different clients that connect directly to the internet. And from there, they connect to the VPN servers, usually at your corporate headquarters that's represented by those buildings at the bottom. This is, of course, a very high-level architecture, but in the upcoming slides, I'll get into more detail and show you the routers and such. Now, this is the client-to-server dial-up architecture, and you'll notice not too much changed. This is the VPN architecture, this is the dial-up architecture. The only thing that changes is the network. Instead of using the internet in a VPN architecture, you use the PSTN, the Public Switched Telephone Network, sometimes called POTS, plain old telephone service. So you can see from a high level, the difference between the dial-up and VPN remote access systems is really negligible. The only difference is the backbone that they use to connect. Now let's dig a little deeper and look at them at the low level. This is where you're going to start to see a lot of differences. This is the detailed architecture that a VPN client uses to connect across the internet to your internal network. On the left here we have the client computer, of course, and it connects through some sort of router. This isn't any specific router. This could be your home router with a built-in wireless access point, or it could be the router at a hotel. And then, of course, that router connects to the internet. So this is exactly the same as all internet traffic. This over here is your corporate headquarters, or wherever it is your VPN server is located. Of course, you have a router to connect to the internet. You probably also have a firewall that filters and monitors traffic. Now, when the VPN connection comes in from the client through its router and through the internet and then through your own internal router at the headquarters, the VPN will look at this VPN traffic and say, all right, this could be a legit VPN client. I'm a firewall. I don't know how to authenticate VPN clients, but I know somebody who does. So I'm going to forward that traffic over to the VPN gateway. The VPN gateway up here is responsible for authenticating the client and then authorizing the client. So it'll require some credentials, which it forwards onto a Radius server. And if the client checks out, then it says, all right, I know who you are now. Are you allowed to access the VPN? If so, then it establishes a VPN connection and begins forwarding traffic over to the internal network. I've represented the internal network by this servers block over here. Now, this isn't the architecture that everybody uses. You can see here, I've configured a multi-homed firewall and established the VPN servers on one network hanging off the firewall and put the servers and other internal resources on another connection from the firewall. But different organizations use different architectures for the firewall component of it. But they'll all have this general architecture in common where the internet and routers and firewalls separate the client from the VPN gateway. Now let's take a detailed look at a dial-up connection. And you'll see that really it's not all that much different, except that, of course, you still have the internet connection because none of us are going to live without the internet, right? The client isn't using this. Instead, the client is connecting to the public switched telephone network here. And instead of using a router, the client is using a modem. Now, if you're an old guy like me, you know exactly what a modem does. It's the modulator, demodulator, and it makes funny sounds like ee, And back when I was a boy, I used to connect to bulletin board services with a modem, and I had this 300 baud modem. That's how old I am. And it made all these terrible sounds, and nobody else could use the phone. And if somebody went to pick up the phone, of course, it would disconnect my connection. And later we upgraded to faster and faster speeds. But nowadays modems, they're much faster, but they're still pretty slow compared to the speeds you get with a broadband internet connection. For that reason, they're not all that common. So the client connects to a modem. This would be done with, it could be a USB cable or a serial cable, but a lot of clients have modems built directly into them. If your computer has a phone jack on the back, looks like an Ethernet cable, but it's a little bit smaller, well, then it probably has a modem built into it. But nowadays, people use modems so infrequently that if you need to use a modem, you're probably going to end up buying a USB modem. The modem itself connects to the public switch telephone network with a phone cable, just like your old school home phone does. It's exactly the same thing because it's doing exactly the same things. It's basically taking all the network data, all the bits and the bytes and the IP headers and such, and turning it into audible sounds that can be transferred across the PSTN, because the PSTN is designed to transfer not data, but your voices and sounds. So the modem just takes bits and bytes, turns it into sounds, and puts some checksums in there, and then sends it across the public switch telephone network, which creates a dedicated circuit to the destination. And at the destination, there's another modem, but more likely a bank of modems to allow multiple people to dial in at the same time. These modems take those audible sounds and turn it into bits and bytes, IP headers and packets and data, and from there it goes back to being a regular IP communication. It can be sent through the firewall. It could be routed through a router and back out to the internet. If this client wants to access the internet, they could do it through this modem and PSTN connection. Believe it or not, some people still use modems and dial-up connections for internet access. But if they're accessing the internal network, the router will make sure that the traffic goes to the internal network and gets forwarded back to the client. Nowadays, modems vary in speed from, well, the traditional analog modem with the funny sounds was about 56 kilobits, but overall that was a wild exaggeration like most networking terms, and you'd probably be lucky to get half that. And that's kilobits, not megabits or gigabits. So that's pretty slow. If you have a more expensive digital ISDN connection, you can get 128 kilobits. You can gang together multiple connections to get some multiple of that, but it's pretty expensive. Now, me at home, I have a cable modem broadband connection, and I get about 35 megabits. So that would be 35,000 kilobits versus about 30 kilobits. So you can see for me, it's 1,000 times faster for me to use my broadband at home than it would be to use the fastest of dial-up connections. And for that reason, dial-up connections are going away pretty quickly. I teach them here because the Sstpd certification exam wants you to know about them. And heck, it's a little bit of history, right? You get to know what it was like being me growing up. Now, up until now, I've been discussing client to server architectures. This is one individual or a group of individuals connecting to one server or a group of servers. But there's another major architecture, and that's the site-to-site architecture. If a company has offices in 3 different locations, well, they don't want all the users in Office A to be establishing separate VPN connections to the headquarters, right? They really want one big VPN connection to link the different headquarters, so that's what they'll do. So this is a site-to-site VPN connection. All 3 of these offices will have internet connections because we all need internet connections nowadays, right? Well, because they all have internet connections, they'll just use the internet to talk directly to each other. And they'll configure VPN servers to route traffic across the internet using a virtual private network, just like routers would do if they were connected directly together. In fact, most of the time that capability is built right into the router, though many people still do use separate VPN devices. And this is what a site-to-site connection looks like if you're using the good old PSTN. Once again, I'll flip back and forth. This is VPN, this is PSTN. They look exactly the same at a high level. They're just a slightly different network. The internet, feels kind of scary because you've got scary stuff going on the internet and criminals and such. Back in the day when we were first introducing VPNs at the company I worked at, BBN, a lot of people still preferred to use PSTN connections because they were just tried and true and trusted, and they felt like they literally got their own private set of copper wires traveling from one office to another, and nobody could snoop on it. Whereas if you were using a VPN and the traffic was going across the internet, you didn't know exactly how your data was going to get from site A to site B. You didn't know which ISPs it was going to travel through, and you didn't feel like you necessarily trusted all those ISPs. Now, of course, VPN stands for Virtual Private Network, and that private component means everything is authenticated and encrypted. But, back in the mid to late 90s when I was working at BBN and trying desperately to sell VPNs to people, they got pretty anxious about this, and they said, "You're telling me you don't know which networks, which ISPs my traffic is going to travel through, and you expect me to trust it?" And we'd say, "Cryptography, math, algorithms, encryption, all this stuff. Trust it, really?" Well, people don't trust stuff until it's been tried and true. And now it's many, many years later, gosh, almost 20 years that I've been doing this, and now people do trust VPNs, and in fact, The PSTN is generally considered just way too slow and way too expensive, but you can still use dial-up connections to connect different offices across the good old PSTN. So let's zoom in a little bit and take a look at the site-to-site VPN architecture at a detailed level. Over here you see a bunch of employees with their laptops over at site A, and most of the time they're probably connecting to file servers on their local network. They probably have an intranet server set up here with their cafeteria information and the phone numbers of all their employees. And if they go to access the internet, their traffic goes through the firewall and then the router, and then to the internet, and then of course responses go back to them. Now, what happens if they need to access these servers over in site B? Well, in this case, this router will know that these networks are not accessible on the general internet. But the router will know that it can get traffic to this destination if it goes through the VPN gateway. So it'll actually send traffic back to the VPN gateway. The VPN gateway sticks all that data into an IP tunnel. It just sticks it into another IP packet along with data from other clients. Well, they wouldn't be sharing packets probably, but they would be in the same stream. Then it adds a destination IP address of this remote VPN gateway. So while this client is addressing this server, the router knows better. It knows it needs to send the traffic over to the VPN gateway, and the VPN gateway knows that it needs to address the traffic to this VPN gateway. So with that destination address, the traffic can now travel through the internet to this VPN gateway. This VPN gateway knows the VPN connection, and it pulls the data out from inside of it and sends it over to the server. Of course, the server responds and says, here's your data, puts it into a packet directed directly to this client. This router says, oh, I cannot reach that client across the internet. I have to send it back to the VPN gateway. The VPN gateway knows it's a response to this VPN gateway and addresses it directly to this VPN gateway's public IP address addressable on the internet. And that's how communications go. Now, I've drawn separate VPN gateways here, but in the real world, more likely, nowadays, those VPN capabilities are built directly into the router. So most new routers, even consumer routers, will have VPN capabilities built right into them. Back in the 90s and even in the 2000s, when I was working for BBN and trying to sell these VPNs, they were separate devices, and in fact, they were quite expensive. Now there's open source VPN software, and so you can just stick it into any $30 consumer router, and all the capabilities of those $10,000 pieces of equipment that we were selling are basically free for you to use, and most of us don't even know how or care about it, but they're there and it's readily accessible. So for that reason, everybody should be using site-to-site VPNs now. And you can trust me when I say that, because I'm no longer selling them. I don't make $1 from it. Now I'd like to dig into the various VPN protocols a little bit, because when you set up a VPN, you do have a variety of different choices for authentication and encryption, and you should be familiar with those options and the benefits of each. Up first, my favorite new protocol, IPsec/L2TP. IPsec, just so you know the term, is a working group, and the IETF is the International Engineering Task Force, and they make all these standards that the internet runs on, basically. They're called RFCs. So the IPsec working group, a group of quite nerdy engineers who deal with the bits and the bytes of how stuff gets transferred across the internet. They've created a bunch of different RFCs for all sorts of internet communications, and they're all, as a group, called IPsec. Part of this is called the Layer 2 tunneling protocol. So L2TP is basically part of IPsec, and when we say IPsec, we don't necessarily mean L2TP unless you're talking about a VPN. But when we say L2TP, we're definitely talking about an IPsec standards-based VPN. All these RFCs I'm talking about, they're all just public information, so any VPN vendor can just look at the standards and create a software or hardware-based VPN that complies with those standards, and they can expect compatibility with other devices. There's no licensing fees that you have to pay. It's just free and open source, and that leads to just wide compatibility and wide support. And that's the biggest advantage of L2TP based VPNs, is you can connect your Apple computer to it, your Windows computer, your Linux box, your FreeBSD, whatever bizarre device, mobile devices, Cisco routers, all that. They all support these same standards because they're basically free to support. Now these nerdy IETF engineers that I was talking about, they're brilliant. And one of the things they've done with L2TP is to provide for any sort of encryption that you want. So L2TP doesn't have to work with one particular algorithm, though there are a set of encryption algorithms which are commonly used. And the most commonly used encryption algorithm is 256-bit. That provides way more than enough encryption. 256 bits is a lot. So if you were to manage to capture this VPN traffic, if you're using a sniffer and you're watching somebody else's VPN communications, you can look forward to several thousand years of computer hacking before you could actually access their VPN traffic. So prepare your sneaky self for some patience and time before you can actually read that data. One of the big advantages of L2TP is this kind of add-on standard called Ipsec Nat Traversal, shortened to Nat-T. I told you the working group throws out a whole bunch of different standards related to Ipsec and L2TP. So when network address translation became common, they packaged up a standard that would let L2TP get through these increasingly common NAT devices. I've discussed it in other lessons, but for review, a NAT device sits between a bunch of clients on an internal network and the internet, and allows all these internal clients to share a single public IP address. That makes it a little difficult for them to receive incoming connections, specifically VPN connections, but NAT Traversal works around that and just makes it work without you worrying about it. I'm going to tell you the port and protocol numbers for all the different VPN protocols, and I hope you'll never have to know these. I had to learn these because back in the day you had to configure a firewall to allow the VPN traffic through, and you'd have to go in and manually configure every port and protocol number that it used. So this was really common, and over time you just memorized it. And then when people started testing you for certification exams, they thought, well, these people who have been doing this in the field, they have learned these UDP port numbers and these protocol numbers, and oh, I'm writing a test, and it's really easy to test if somebody remembers that L2TP uses UDP 500 and IP protocol 50. So they started writing test questions around these port numbers. I don't endorse this, and I wouldn't write test questions that simply forced you to memorize UDP port numbers because it's so easy just to search and look this up. But I do want you to be familiar with these port numbers, not because you need to memorize them for the real world. They're easy to look up. Save your brain storage for something else. But for the certification exam, I wouldn't hate it if you wrote these numbers down on some flashcards and remembered them just in case you see them come up. You might see a question like, which of the following protocols is required for L2TP? And they'll say TCP 80, UDP 500, IP 50, and UDP 777. And you'll know that of those, UDP 500 and IP protocol 50 are required, and you'll get the question right. It's a fairly useless bit of trivia, but like I said, it becomes practical once you start taking the certification exam. So L2TP uses UDP 500, 1701, and 4500. Now, why does it use UDP and not TCP? As you might recall, TCP, the Transmission Control Protocol, is connection-oriented, and if a packet gets mangled or dropped in transit between here and there across the internet, well, TCP acknowledges this, it figures it out, and it resends that packet automatically without the application having to figure it out. UDP, on the other hand, is faster, but if something gets lost, it's just gone forever. So why would something critical like a VPN use the UDP protocol? Well, the answer is that the VPN is tunneling other traffic, and that traffic that's contained within it, well, that traffic is probably using TCP if it needs to be retransmitted. So UDP is faster and doesn't retransmit stuff, but the VPN itself doesn't need to retransmit anything, because if something gets lost, the protocols inside the tunnel will notice the loss and retransmit automatically. So packaging a VPN protocol in TCP is redundant. It's adding 2 layers of protection, extra headers that are slowing everything down, extra checksums and chatter. Anyway, using TCP for a VPN would make everything noticeably slower, which is why they all use UDP whenever possible. Now, I'm not just babbling on. This is going to become important as we investigate some other VPNs, so just keep that in mind, and I'll talk a little bit more about it later. The only other protocol is IP Protocol 50. Now, most of the time we talk about protocols, we talk about TCP and UDP because web apps use TCP port 80 and DNS uses UDP port 53. Well, IP protocols are a layer below that. IP protocols exist at the OC layer 3, while UDP and TCP exist at OC layer 4. Now let's talk about my favorite VPN protocol to say, BPTP. All right, it's not my favorite to use, but I always liked saying BPTP, point-to-point tunneling protocol. This is now a very outdated protocol, but there was a time when it was actually more popular than L2TP, and as a result, it's widely supported. The encryption is also flexible, but most of the time it's using a less secure 128-bit. Some implementations have security vulnerabilities that allow it to be cracked much quicker than would be typical of 128-bit encryption, so it's not always secure, but the encryption protocol itself is pretty flexible, and the security level of it depends largely on the vendor who's implemented and how they've implemented it. So I can't tell you if any particular PPTP implementation is secure or not, but it does vary. Anyway, it's never quite as bulletproof as L2TP. PPTP is based on the old school PPP dial-up networking protocol, which is what you would generally use when you're establishing a modem connection from a computer to a remote access server. PPTP uses TCP port 1723 and GRE, which is IP protocol 47. Now, in the previous slide, I was talking about all the benefits of using UDP for VPN technology. Notice that PPTP uses TCP, and some other VPN protocols do. This means it simply got more payload, and I don't know why they decided to use TCP, probably because it was required for the PPP-based networking that they were doing. Anyway, it's not a great design choice, and it means that it's got some additional overhead that you wouldn't get with L2TP, and therefore worse performance. So security is not as great, performance isn't as great, still widely supported, but overall I am just going to tell you to avoid using PPTP. If you have some really old client that doesn't support L2TP, then I guess that's your only option, but I haven't seen a client that didn't support L2TP since, the early 2000s. Now here's an interesting and fairly new protocol, Sstpd, Secure Socket Tunneling Protocol. And this is never plan A. SSTP, however, is a fantastic plan B. Now, if you might recall, when I was talking about L2TP, I talked about how you configure the firewall and how it had like Nat Traversal and stuff. Well, that is important because not every firewall is going to support L2TP, nor is it going to support PPTP. Those could both easily be blocked at a firewall, and sometimes that's done intentionally because the person managing the network doesn't want VPNs going across their network. Maybe they want to be able to inspect every packet, and a VPN keeps stuff secret. So SSTP does something that's kind of sneaky. It takes a VPN and pretends it's secure web traffic. Like if you were to go to your bank website, it would use HTTPS to encrypt all your web traffic and make sure that your account numbers and such wouldn't be seen by somebody sniffing traffic. Uses TCP port 443. Well, SSTP just pretends you're visiting your bank's website, except it's actually tunneling VPN traffic to the destination. So the firewall just thinks you're browsing the web, but you are actually accessing files or running remote desktop or whatever it is you want to do at the remote destination. Therefore, it works across basically any firewall. That's right, the firewall at that Motel 6 that you're staying at, and the firewall at the airport, and every mobile access point at your friend's house, no matter how old, no matter how terrible, no matter how secure, SSTP is pretty much going to work. As I mentioned, TCP isn't great for VPNs. It provides an unnecessary level of overhead, slows everything down. UDP simply is better, except that UDP wouldn't travel through some firewalls. TCP 443 HTTPS is always going to get through. That means SSTP provides the greatest level of network compatibility if both your client and server can support it. As I mentioned earlier, it bypasses all sorts of network level security. So if you've cleverly configured your firewall not to allow BitTorrent and instant messaging and whatever other protocols that you're concerned about, Well, if somebody establishes an SSTP connection from their client to some server on the internet, they're going to bypass all of that. And they're going to get unrestricted access to any protocols and apps that they want to use. They'll be able to do anything. All they have to do is establish an SSTP connection. You, as the network manager, can't see the traffic. You can't filter the traffic. You can't restrict the traffic. So in that way, it's kind of scary. You give up all control just based on this secure protocol existing, and this happens all the time. So you can't necessarily lock stuff down on the network anymore. If you want to prevent your users from using a VPN to connect to their home network and then do whatever they want, whatever malicious things they might want to be doing where they want to hide their tracks, well, you'd have to lock the client software down. You'd have to restrict access to the network to only devices that you had hardened and restricted from running protocols like SSTP. If you let anybody connect their random device to your network, they'll be able to use SSTP to tunnel over to some other host on the network and then do all sorts of malicious stuff. Now, there's a new emerging VPN protocol called OpenVPN, and as the name indicates, it's open source. Now, because it's new, it's not so widely supported, and even in recent versions of Windows, you would have to install some client software. It supports 160-bit or 256-bit encryption. Here's the nice thing, it's really fast. Because they had mobile devices in mind, they specifically wanted you to be able to use your Android or iPhone or Windows Phone or whatever device it was that didn't have a big, powerful computer CPU in it. Well, they wanted you to be able to get a reasonably fast VPN out of that. Now, you can use L2TP and PPTP and SSTP with these mobile devices too, but the process of encrypting all that traffic is going to be burning a lot of cycles, using up your battery, and slowing your mobile device down. OpenVPN will do a little bit of that, but it's faster, it uses less resources, therefore it's well optimized for these mobile devices that we're using all the time. Now, in the past, I've required you to memorize some UDP and TCP port numbers for the different VPNs. Well, OpenVPN can use pretty much anything. It can use UDP or TCP. And if you need to bypass a VPN, you just configure it to use TCP port 443. In that case, it looks exactly like HTTPS and the firewall will allow it straight through. So OpenVPN is basically unstoppable, not widely supported, but very fast, and the encryption so far seems to be solid. I haven't seen any hacks for it, but it's one of these things where it's still kind of new and maybe it hasn't gotten the investigation that it requires. So I'm not going to say that it's secure because something could come along, but seems okay. We'll see. Now let's talk about SOCKS. SOCKS is now a very outdated protocol, and I just want you to be familiar with it. It's a session layer protocol. This is above TCP and UDP, and it's probably the only example of session layer protocols that I can even think of that's OC layer 5. It routes packets through a packet server. Back in the old days, the 90s, when I had to manage Unix-based hosts, you would use SOCKS to tunnel traffic from an app through another channel. So you'd say, hey SOCKS, I want you to set up port 123 on this local computer to tunnel traffic through the proxy server and to my destination. And then you'd configure your app to actually talk to port 123 on the local computer. Well, that's a high-level overview of what it does. It's kind of a manual per app VPN. In other words, it doesn't tunnel all traffic for every app on the computer, but you configure it for specific apps on the computer. And, well, it's a real pain to configure, and it's now completely outdated. I would never recommend anybody use it, but there are still a few computers out there using it. This dates back to 1996 and RFC 1928. Look, back at those times, it was all we had, so we used it fairly frequently, and I wanted you to be familiar with the term. That's what SOCKS is, and it's what it does. It's a per application VPN that's kind of manually configured, but it's not going to be the right answer for anything unless the question is, if you're Tony in 1998, which VPN protocol would you use on a Unix server? And that doesn't seem like it's going to come up on the certification exam. Now, I've talked about radius servers in other lessons, but because this lesson deals specifically with remote access, I want to review a couple of key points about radius servers. Here we see three different hosts: a remote user, a network access server, and the radius server. The Radius server is responsible for the authentication. So it can take somebody's credentials and determine whether or not they're an authorized user of the network. Sometimes the Radius server has a user database located on the local computer. More often than not, the Radius server is actually sending off another authentication request, either to another Radius server or to something like an Active Directory domain controller, which contains all the various user accounts and passwords. The network access server is intercepting every request to connect to the network and requiring that the person authenticate. But it doesn't do the authentication. It sends it over to a central Radius server. So you probably have 100 different networks or 100 different VPN servers or 100 different dial-up modems. Well, these are your network access servers. They don't all want to have user databases stored on them, so they all talk to this central Radius server. In other words, the Radius server is the centralized authentication mechanism for all the different network access servers that you might have. And this is how the connection process works. First, the remote user initiates a connection to the network access server. For wired local networks, this could be connecting an Ethernet cable to a switch that has the 802.1x network authentication protocol configured. This could be a client connecting to a wireless access server that's been configured to use, say, WPA to Enterprise, which authenticates with a Radius server, as opposed to something that uses a pre-shared key like WEP. So after the user connects to the network access server, the network access server says, hold on a minute, I need to check who you are and make sure that you're authorized. So send me over a username and password. The user provides their credentials, and then the network access server sends an access request to the Radius server. Basically it says, hey, this guy wants to connect, here's the credentials he gave me. The network access server and the Radius server authenticate each other. They basically have a pre-shared key, a secret key. It's old school, but it's a password that you type into each of them. This tells you just how old this Radius technology is. It's really old. And at the time, the best security we could come up with was, I don't know, type the same password into every one of them. This kind of gets to be a problem because you can literally have hundreds of network access servers and dozens of different Radius servers, and you have to keep the exact same sequence of letters and numbers typed into all of them. So if one of your admins leaves, you need to go update everyone so that he doesn't know your Radius server key. Anyway, the network access server sends the access request to the Radius server to see if the user's okay. And then the Radius server responds with one of two messages, access accept or access reject. Of course, if they're accepted, well, the network access server replies back and says, welcome to the network, and then it establishes a network connection. On a local area network, the network access server would configure the client to join the VLAN. If it was a VPN, the network access server would go ahead and establish the VPN connection. If it was a dial-up modem, the modem would accept the connection from the dial-up client. Now let's talk about some risks of using Radius. First, the communications between the network access server and the Radius server are not encrypted. Again, Radius is a really old protocol. We used passwords and we didn't use any encryption. That doesn't mean that stuff's not going to be encrypted. It just means you need to use some higher level encryption like IPsec or a tiny VPN between the network access server and the Radius server. And because authentication between the network access server and the Radius server is done with this pre-shared key, a password, it means that it's vulnerable to things like spoofing and replay attacks. Something with access to the Radius server, something that could send network communications to it, could also perform a denial of service attack. Just send a whole bunch of requests to the Radius server to handle, and the Radius server has to kind of think about each incoming request, which slows it down. So you can just flood it with requests, and then it won't be able to receive legit requests, and suddenly you have no more network access. So what does this mean? Well, it means you need to monitor your incoming connections to either your network access servers or to your Radius servers. And if you see yourself getting flooded, well, you need to do something about it. You need to route those packets away, or you need to configure enough network access servers and Radius servers that you can withstand a distributed denial of service attack. And because Radius uses the MD5 protocol, there are vulnerabilities with MD5, and it's going to be vulnerable to those just because it's the underlying protocol. You can mitigate these risks. Of course, you harden the Radius server, keep the software up to date, use firewalls to block all unrequested traffic, specifically only allow traffic in from authorized network access servers, limit access to specific IP addresses that you've deemed okay to send requests to it. Because the authentication isn't great and the encryption is non-existent, you need to use other protocols like IPsec or SSL. Basically, you need to use another lower level protocol if you want security between your network access server and your radio server. And you know what? You do want security, so do that. You should also choose a unique shared secret for each network access server. That means each network access server has its own private password with the radio server, and if you have 10 network access servers, you have 10 different passwords to manage. Makes everything more secure. If somebody hacks into one network access server, well, they only have the password for that one connection, and you can just change that one password without disrupting all the other network access servers. I've touched on this in other lessons as well, but I'm going to review thin clients because they're specifically mentioned in the SSCP objectives for this topic. So thin clients are in contrast to a traditional PC. Traditional PCs have a big old hard drive and they have lots of memory and a fancy graphics card, and most of all they have this big expensive processor that's capable of just cranking through billions of numbers a second. That's great if you are rendering video or running complex Excel spreadsheets. But nowadays, so much of our processing is done on remote servers. Well, thin clients are designed around this client-server architecture. And basically, they have very cheap, lightweight hardware. They have inexpensive, low-power processors. They have very little RAM and video memory. If they have local persistent storage at all, it's probably not a hard drive. It's probably a tiny bit of flash memory. Sometimes it's 256 megabytes of memory that just stores whatever lightweight operating system it needs to load up. Doesn't mean they can't do things like play video or play games, but they're going to be communicating with a remote server to do all the processing, and then they basically just display it on the screen. Of course, there'll be a keyboard and mouse there for user input, but they're not even processing those signals. They're just sending it all back to the server for processing. So this is a method of remote access because you have a big server and you're using a cheap, thin client to access those remote resources. These have been used in the enterprise for decades just because it's cheaper and more efficient to run one big server with 100 tiny clients than to run 10 big, expensive, powerful clients and have all their software local. As long as you have persistent network connections, the thin client architecture works out wonderfully. They're starting to come to the consumer world as well. Google Chromebooks are basically thin clients. You can buy a full-featured laptop computer for about $200. And it has a terrible, tiny little processor in it, but it doesn't really have to do much processing because it's relying on the remote server to do all the work. So that lets you get a laptop that would probably cost you $600 to $800 if it was running Windows, lets you get it for about $200 because they can use cheaper hardware inside of it. So let's talk about the pros and cons of thin clients. The pros are, well, I just told you it's cheap, and that's great, right? It also provides centralized administration because all the hard work is being done by a centralized server. So if you need to update the software, you do it on the central server. Everything's in one place, and I can't tell you how much easier it is to manage one big server than 100 clients. It also greatly reduces the risk of client-side malware. After all, if all a thin client can do is display a video feed from a remote server, well, it's probably not going to be susceptible to malware. It doesn't eliminate the risk of malware. They still run some bit of software that could get infected, but the risk is much lower because the attack surface is smaller. There are some drawbacks. Well, you can't get much done offline, right? If you're required to connect to this big server on the network and you bring it on a train where you have no network access, well, you're not going to get anything done. Sometimes they'll have lightweight apps that can run locally without network access, but they pretty much require network access for most of the heavy lifting. That means you also need some sort of server infrastructure. You have 100 clients coming in, well, you're going to need a pretty big server to manage all these incoming connections. It's still more efficient than creating 100 separate powerful client devices, but it's something new to manage and probably new apps for you to learn. Not every app will work on a thin client. Most of the big apps, though, do work. All the Office suite is designed to be used with thin clients. Microsoft has a whole set of technologies around it. Of course, any web apps will work beautifully. Those are necessarily designed to be thin clients. Even apps that traditionally require a very powerful client-side computer like 3D gaming, there have been some recent technologies that allow these to be streamed across the network. Therefore, even things like gaming and video rendering can be done on thin clients, but you do need an app that's designed to support it. Another con is that all these clients depend on this one device. That means you have one big point of failure, one big target for an attacker. If you hack that one server, well, you hack all the apps, and therefore you hack all the clients too. If you perform a denial of service attack on the server, guess what? None of the clients are going to work. So you could attack one spot and break 100 computers. Thin clients aren't especially resilient in that way. You definitely have better availability with 100 powerful computers each running local apps because the processing is distributed. This is Tony Northrup for Train Signal, and thanks so much for watching this video lesson.